I'm Marcos from Brazil. Just let me adjust here. And I'm going to present my master thesis right now. I hope you enjoy it. It's about self-driving cars and with autonomous driving open source platforms. So let's go. The title is an applied study of ROS-based autonomous driving platforms to carry out automated driving functions on different scenarios. I am from Brazil, Joinville. It's the city where I have developed this master thesis in UFSC. That it's a huge university in Brazil, the first one inside an industry complex. So the university is surrounded by a lot of industries. It's a very nice idea from this Brazilian university, and let's go. Okay, so now I'm going to outline the problem statement, that is navigate autonomously using autonomous vehicle from the origin to the destination, avoiding obstacles. This is the basic goal from any kind of robot, and the same for a car like robot. So this is one of my simulations that I have used Apollo Auto framework. So just let's check this video. As you can check, the car have avoided the obstacle and it's navigating to San Francisco City. And in Apollo it's nice that we have these dynamic graphics here, dynamic charts that we can check the vehicle behavior, and yeah, we will check this framework later. This is just an introduction for what we are going to see in this master thesis. So let's go ahead to the next slide. Some issue that the slide is being reproduced again. Let me check what's okay. So my specific goals to I have drawn this framework here to reach the final goal. That's the problem statement. But before talking about my specific goals, I just wish to share you from YouTube. That's this. I have recorded this video for the students that like ROS, that would like to develop their self studies in this area using ROS and open source platforms. So my master thesis was presented. I had just 30 minutes to present it, so this video is going to reach more time. I expect about 1 hour or more maybe, because I'm going to say step by step for what I have done, so you can skip in the video for the slide that you have more interest. And then it's not a short video, and my master thesis is not I will make available also a link with the discussion with the board of examiners. So this presentation is just for YouTube, and the professors that like can also share later with the students. So let's go to the steps. The problem statement, that is study available open source frameworks to carry out automated driving functions. That's the same of the title. So we are going to cover a lot of different frameworks that I have tested to read that goal that you have checked it. Okay, so for that I will do simulations using these frameworks, and we will discuss was this framework able to perform the autonomous driving function? If yes, we will go ahead with select the framework and test the framework's trajectory planners, because our specific goal here is to go deep in the trajectory planners features, not the perception or localization or mapping module. Of course, we will check these modules too, but not with deepness, and discard the ones that was not so useful. Okay, then later I will implement different scenarios. I will code different scenarios to test the trajectory planner and decision making behavior. And finally, we will check if the planner was able to calculate the trajectory with safety in this scenario. If yes, we will go ahead and record the data. If not, we will just discard the data because the car collided and this is not interesting for us in this moment. Because we will just compare the path planners that had feasible solutions and not the scenarios and the path planners that didn't pass and didn't guarantee a safe trajectory. Maybe later in another work I will go deep in this. In the book these issues, but okay, so let's, and then after recording this data I'm going to extract the data to further assessment. And of course, because the data is the raw data from a lot of different sensors, and when you record a ROS bag or a cyber bag or a cyber recorder, you have a lot of hard data to deal with, and then you need a little of data science to process and give value to this data. And this is to be honest, this was the one of the hardest part of this master thesis. And finally, I will get this data and do a benchmark, not just from the path planners, but also from the frameworks I have used. So I hope you enjoy this work and learn a little bit more from autonomous driving stacks. Okay, so let's start to the motivation and introduction. Okay, so the motivation. Unfortunately, 94% of road accidents are caused by human error. So the problem is us, the human being, not the machine, not the engine or mechanical problems. As you can check by this information, you can conclude that. And there is a close relation between the human error and the driving tasks. In other words, some specific tasks, such as parking, there is a close relation with the human being and that performing that task. If the guy has some motor problem in the arm, for example, or have some disturb, he will suffer an accident in a specific driving task. There is a relation, and there are a lot of studies that I won't cover here very deep. This relation is just for you know that a specific task is related to a specific human. I will not say disturb, but you got the idea, I believe. So these images will facilitate the understanding. So for example, if there are very swerve scenario, the curve is very harsh, so it's hard to control, and this is specific task and a specific human being that is not used to drive in this situation. For example, a lot of us is not so used. No, we are not how can I say, a competitor, and we are not used to deal. We are not trained with race cars, for example, to deal with this curve, so it's hard. People that have sleep issues and don't sleep very well, and get asleep very easy, so this can cause an accident. Elder people that they have lose some skills, and they face also more problems to drive. As you can check the blind spot, also the pedestrian that's not paying attention in the traffic, so he will probably let the other drivers crazy and he will suffer an accident, maybe, I don't know. A bad parking, if these issues can be solved and were solved, a lot of them by the advanced driving systems, and this is the contextualization part. So we can check that the automotive industry have developed the passive safety systems that, okay, if you suffer the accident, we will guarantee that you harm less, and probably you will survive. So that's why we have seat belts, airbags, and so on. And the active safety systems, that is ABS, the electronic stability control, and the other. To be honest, I forgot not the meaning, but all the pronunciation of each of this letter. What's the abbreviation? But you can just check this later in the internet. And these systems were invented decades ago, but are still used. And then we finally reached the advanced driving assistance systems that I was, before showing these images, I would like to. I was very lucky to be able to do an internship in this field. I have done an internship in Audi, in the radar system, so I cannot share all the self-study program, but so here I have done in the radar area. So this is just a sketch of the radar, that he sends a wave and receives a wave, and then the car knows the obstacle, how far the obstacle is, and then the emergency brake starts stopping the car and control the velocity of this car. And I wish to say thanks here to Audi, because I was able to learn a lot. They have a self-study program, as you can check here, just for internal use, so I cannot share this material. But it's a very nice enterprise to work if you wish to do an internship or look for a place to work. Audi is the right place. It's amazing. You have I had a good supervisor. I had good friends there, and they don't press you a lot. They are your friends and help you, and everyone grows together. It's a good mindset. It's a positive pressure, not a negative pressure. So I was very happy and very lucky to do this internship there. And they have a very nice self-study program. This is what I can say. And the relation with the contextualization here is that not just Audi but BMW, also the Volkswagen, Tesla, Fiat, a lot of these huge industries are employing the ADAS more and more and developing more the technologies that go to the ADAS to ensure more safety for the drivers. Okay, so as we can check, we have the active lane departure warning, advanced driver system that is the system emits some alerts for the driver, maintains the the vehicle in the center of the lane if it's escaping to the other lane. The intelligent headlamp control, that is an automatic control of the intensity and the range of the lights during the night, so this avoids to disturb the other driver that is in the opposite lane, and even avoiding accidents for this case. Emergency brake assist, that the car just brakes autonomously when a pedestrian or other vehicle in the front of the Eagle vehicle is pretty close, and then the speed is reduced, or even the car is even stopped. Driving monitoring system, it's very important in the new models of the vehicles, because monitor the driver's face and the conditions, if he is sleeping or he or she is not feeling well, it's not paying attention, so it sounds some alerts or talk to the driver for he takes a place and to park the car. The blind spot, to avoid that the car changes the lane if the other vehicle coming later into the car's back, and the driver didn't see because of the blind spot. The car emits some sound alerts to say, hey, change the lane later, now you are going to hit the other vehicle if you try to change in the lane. And the rear, the same, if the car is leaving the parking spot, also an alert says to the driver stop and do this later, to avoid to crash with other car. Now we have checked the anti-lock brake system, the other active safety and active safety systems, passive safety systems, then the ADAS, and now the evolution is the autonomous driving, the ultimate level of automation, and we will check this right now. This contextualization, this level of driver automation is based on the Society of Automotive Engineers. The level 0 is no automation. The driver must do everything. The level 1, the driver has some assistance, such as active cruise control. Level 2, the car has lateral and longitudinal control from the system, so it helps the driver maintain the vehicle in the center of the lane, avoiding more accidents. And level 3 is conditional automation, then the driver can disengage from the driving, but the driver must monitor and must pay attention to the traffic, because anytime the car can say that needs the driver's in the steering wheel, because it's not able to drive in that specific situation. So there must be a monitoring system in this with this level of automation. So level 4, just the driver does not need to control the vehicle in a lot of scenarios. Just in very rare scenarios and occasions that is specific operation design domains, the driver must take the control. I believe that these specific cases are, for example, places without HD map, without roads in the farm that does not have traffic signs, have a bad signalization, and have or some harsh environmental conditions with a lot of snow, some things like this, that the perception doesn't work very well. I'm not sure which specific code it is, because I didn't find in the literature, but I believe it's something on this regard. And the dreamed level is that's fully automation, and no driver is required. So the car will not have steering wheel or gas brake pedals. I believe we are not so so close but not so far from this level of automation, then in some years or decades we will have this. But I am not an expert. If you wish to get more information about this topic, I really recommend you watch this video that I'm going to share. That was my professor from ADAS and autonomous driving, one of the leaders in Germany from this topic. And he claimed he can explain with more property these features. I really recommend. And you can just see.
Up to now, the question is clear, the answer is clear. It's a driver, but this could change in the future. Let me start with this classification of use of automation.
He explains very detailed. He's a very great professor and professional, so I really recommend, if you wish to go deep in this topic, that you read his articles, and also you can check his videos in the internet. But let's back to presentation now. So returning to the presentation, now we can check what autonomous car how it must behave. So it must centralize the vehicle in the lane, in the center of the lane, perceive the environment, and just go ahead, avoid obstacles. And for that, we need to outline now the sensors that play a very important role in autonomous driving. I'm going to highlight the main sensors applied in ADAS and autonomous driving, and let's check. So now, for the environment perception, the sensors sense the environment, but it's also they are used to classify the type of object. So if it's a truck, if it's a car or a bicycle. But besides the text, the obstacles, it also provides inputs for the localization module. So for example, in Autoware Auto, the normal distribution transform algorithm that they call NDT, the NDT algorithm uses input from the Velodyne, from Plonge Cloud data, and this PCD data helps in the localization algorithms. They are fed with this PCD and to say where the vehicle is located. The main sensors, Elon Musk believes that the camera is the main sensor for autonomous driving. In his opinion, just camera would be enough. Here we are checking the camera doing the function of lane detection. Then in this function, after the camera be calibrated, the camera detects the lane, and so the car can keep navigating inside these lanes. We have also the radar, that is radio detection and ranging. And the radar is also the heart of the autonomous car, because it can detect the orientation and the position, the radar cross-section, the area of the obstacles, the width and the height of the obstacles. The radar is used in a lot of functions such as emergency brake assist and others. We have different type of radars. We have short range radar, long range radar, and medium range radar that they are used for different ranges, as the name says. But the radar can have also other classifications, such as the number of antennas, the frequency, because the radar can work in different frequencies. It depends on the country, the regulations, and so on. It's a very huge topic. It's very interesting. I have done my internship in Audi in this field. What I can say is that it's complex, but it's also in the same time it's amazing. And the radar can perform a lot of ADAS functions also for autonomous driving, because the radar does not depend from the weather conditions. So if it's snowing, it works. If it's raining, it works, and the camera not. Maybe the camera does not work so good if it's snowing or raining. So the radar is more robust regarding weather conditions. We have the LiDAR, that's light detection and tracing. It is use other kind of physics principle. Radar use electromagnetic waves, and the LiDAR use light waves, and then the principle is different, but the functions that it's also similar. That's detect the other obstacles, position, the format, as we can check here, a truck navigating near the eco vehicle. Here, so you can have more accuracy in the position, the orientation. And finally, the ultrasonic sensors that it's more used for parking and autonomous parking, and this type of functionality. The car has 4 frontal ultrasonic sensors and 4 in the rear, as we checked in this video. This was done in navigation stack, not in Autoware Auto. The previous 3 I have done simulations using Autoware Auto, and this one navigation stack. And the ultrasonic sensors use the trilateration method to fuse that is a mathematic a model that it's used to determine where the obstacle is. And it's pretty interesting. Of course, I'm not going to detail, but you can read. I will add the references also in my master thesis and in the video description. Just send me a commentary. I can share the materials if we wish about some specific information of some sensors. I also must suggest that if you wish to understand the sensors working principle with more details, go to the Autoware Auto lectures that they have made available in the internet. I'm going to share now with you. Here, the Autoware Foundation, they have done a lot of great lectures. So you can also implement in as I have done the simulations. So LiDAR, explanation, camera, radar, a lot of HD maps. So they have done a lot of classes with implementations in LG simulator and using Autoware Auto. I suggest if you wish to. I suggest that you go through these classes, online classes in YouTube. And now we go to the last sensor that is considered an additional sensor, that is the high definition map. And the high definition map, if we check here, just 1 minute, because I have pressed some wrong button here. Okay. So in the high definition map we have some information about the environment. that the satellites delivers to us, to the vehicle, such as real-time exploration. The road lane network also gives the semantic, the meaning of the traffic signs, the geometric of the road, so the vehicle, the decision maker interprets the lane network, the signs, and say, okay, there is a traffic sign that obligates the car travels in less than 100 kilometers per hour, so the car will brake alone and not overcome this limit. And this data also says you cannot travel in this direction, and so on. So it's a very, very important feature of autonomous car that the other robots does not need. An industrial robot does not need maybe to have this information from GPS. And the autonomous car robot, this additional sensor plays a very important role. And we can check now in the video a little bit of the traffic signs and crossing area that is the satellite is giving this, is taking this information and sending to the car. So there are the arrows here saying which is the direction that the car must follow. And that's it. The HD map, the high definition map, it's also considered a sensor. Also in the last classes, the last class of Autoware auto course, the last lecture, it gives a deep explanation from high definition map, and it says that the high definition map is present in all the layers of autonomous driving, from perception to the control. So it's worthy to check. Okay. So now we are going to understand the complete model, the whole model of autonomous driving, the architecture. Go to the bibliography review now. We can take a look. I'm sorry sometimes for some missing information or not just accurate information, also maybe for my English, but as I said, this is not a video, this is not my master thesis presentation. It's a more how can I say, a more comfortable talk. And then later, if you wish me that I do other video explaining specific topic, you can just write in the comments, and I can share the information that I have. And yes, this is the goal of this YouTube presentation. So let's go to the main panel. Okay, so the autonomous navigation architecture. So what the autonomous car must have? Just the sensors you told me. What more? How do I integrate these tasks for the cars that drive autonomously? Okay, so let's go. As I said, at first the robot should be capable of sensing the environment. I'll then later interpret this data. As I said, in the HD map, it's the interpreted data ready for the autonomous driving, and later planning a road for the car from the initial position to the final target, avoiding obstacles, and of course control the actuators. For the actuators follow the planet trajectory. This is what other robots do, and also the autonomous car must do. I have done this. I have done this sketch here. That's actually I was doing a paper that I was comparing the autonomous underwater vehicle, the unmanned aerial vehicle, and autonomous land vehicles, then I have done a framework that would be the same for all of them, and that's why it's not so specific for autonomous driving car, but also for the other robots. So the robot must perceive the environment, also the cognition phase, that is, the cognition involves the path planning and obstacle avoidance systems, algorithms, that's the software. In this perception, it's the hardware, that it's also a little bit of software that is for processing the localization, the self-location of the vehicle and detecting environments. And later the operation phase uses the motion control and the trajectory execution. In my outline, is shrinked in this phase, and then send the motion control message to the hard actuators. This is for any robot. This is the basic idea. And okay, but in my master thesis I have focused in the path planning algorithms, because the other each module here, a submodule, has a lot of content and codes and packages and theory that it's impossible to cover everything. So I like the path planning topic, then I have chosen this one to develop my master thesis. So let's focus just on path planning. This is a sketch for autonomous car. It's very similar. That is use computer vision. That's OpenCV, for example, algorithms, sensor fusion. They use Kalman filters, and the car can localize itself using the HD map with these data. Then plan. Then later the path planning must solve the planning problem. Finally, the control algorithms will be responsible to send the commands. I took this sketch from Udacity, that I think they offer also but paid courses for autonomous car, but I have never done. It seems very interesting. But I have heard that to do these courses, they select a person that is able to do this course that have some programming background and so on. So it's not anyone that can start doing this course. I would recommend to start with open source and later start this course. I don't know. Okay, so path planning. What's path planning? There are a lot of definitions for path planning, and they are not very short. There are a lot of different interpretations, but usually path planning has by some properties such as state, time, action, initial and goal states, and a criterion that is how much feasible is the path. If it is feasible and the optimality of the path, it can find a goal or not. And this is the meaning of optimality. The meaning of completeness. So path planning. The feasible path means how much feasible is the path for the car, not for the robot shape, because we have non-autonomic autonomic robots, as you can check here. So the vehicle structure follows the physical constraints of this robot. So the path planning must be feasible for this robot. In other words, must be coded for this robot different codes and different path planners must be specifically developed for a specific kind of robot shape, or otherwise it will not work. If you use a path planner for an autonomous underwater vehicle that have a specific geometric constraints, this path planner won't work for the race car. It's totally different. So the feasibility, one of the means of the feasibility is the feasibility of the path. Maybe our algorithm is not feasible for some scenario, more complex scenario, it does not find the solution, but for other scenarios they are feasible. And optimality is how optimum is this, is about the quality of the path. Sorry, I was wrong. I was talking nonsense. It's for example, an optimum path is, I would say, is the shortest path. Is the optimum path. It's the path that the robot spend less energy. So if the shortest path is 5 meters, an optimum algorithm will find that the optimum path is this 5 meters, and then a non-optimum path will find that will say that will give a solution of 10 meters, for example. So it's not an optimal algorithm because it did not find the best path. And this is the meaning of optimality. There are some algorithms that are optimal and others not. But this also is hard to say, okay, just use the optimum algorithms, because sometimes the optimum algorithms consumes a lot of time and consumes a lot of memory to find the best path. So you don't have this time in a dynamic scenario, and maybe you don't have this computer that consumes a lot of memory every time it's processing data. So not always you have an optimum algorithm working in your robot, for sure. Here's just a classification of path planning, that they are based on constraints, based on previous environment knowledge, that's offline methods, online dynamic methods. So in the offline methods you have a previous map, for example. In an online method you don't have the previous map. The RRTs, usually you don't have a previous map, they just look very quickly to the solution without a map. Having a previous map, you use SLAM, that is simultaneous and localization mapping. Simultaneous localization and mapping, that will go get data and generates the map. So the robot is always generating a map, and the algorithm is always calculating a path. This is an online method. And based on environment, the composition method, that's the deterministic methods, that are some kind of algorithms, and probabilistic methods, that's the RRTs, for example. And the deterministic method is the algorithms that will always address the path planning the path planning problem with the same solution. So in the deterministic method, if you run the algorithm 10 times or 100 times or 1,000 times, it always give the same solution for the same goal position. It will say, okay, the shortest path that I have found is 7 meters. The second time you run it, it's 7 meters again, then you iterate again, and they always will be 7 meters. In the probabilistic methods, it finds different paths in different times you run. In the first time it finds 7 meters, in the second time 10 meters. This is the difference. Okay, I hope you understood. The constraints, as I said, is the geometry of the robot. The car-like robot, the kinodynamic methods and the non-holonomic methods are feasible for these robots because they don't follow the holonomic geometry. They are non-holonomic. And the kind of dynamic methods, they are regarding the velocity and the acceleration constraints. That this is very, very useful for autonomous vehicles, because there are some constraints in the acceleration, the velocity of the robot must obey to address to construct a feasible trajectory. Because if the path is drawn, but the car cannot reach that acceleration or that velocity, or the acceleration velocity is not able to follow that path, because it constrains for the vehicle reach that path in that velocity or in that acceleration. It's not confused, but it's a deep topic that you must understand, that a path and a trajectory must be built respecting the acceleration and velocities limits of the robot, so the path will be feasible. Otherwise, your robot won't follow that path, because the acceleration is higher, the velocity is low, or both are higher, both are low, and for that path it's going to collide. So another path should be feasible, and the algorithm must respect the robot constraints. Okay. So now, path planning. Finally, the basic idea: the origin point here and the goal point here, and this drawing here, it's the global planner, the global planning part of the path planner. That's usually we using Uber or other navigation systems in the HD map or these applications. It's the shortest solution. The global path find the feasible lanes, the feasible roads, and this is how the path planning is divided. So global and local planners. The global planners I have commented yet, and the local planners, they are used to avoid unexpected obstacles. So during your trip in the city, maybe a dog or also another car, a pedestrian enters in front of the car, and then the local planner is the planner used to avoid this obstacle, not the global planner that just say the road that the car must take, the best road. So usually the path planning is split in global and local planner, and therefore they are complementary. Okay. So I have implemented and tested some global planners, and I have implemented all the algorithm in the Robot Ignite Academy. This is the Dijkstra algorithm. That is a very standard algorithm that they use this algorithm to implement the other one. So here this algorithm expand the nodes for all the neighbors, as you can check here, in the front, in the right, in the left side of the robot, and check the shortest path using backtracking, and then found the shortest path. This is a complete solution, so I would say it's an optimal solution, because the robot found the shortest path. And a lot of the other algorithm, really best for search, it's expand the nodes, the cells, with a bias that is just look to the front of the robot, not consider the backward, and use the Manhattan distance or the Euclidean distance for you parameter for you say okay go here and don't go to the other side. So this consumes less memory from the machine you're using, and it's faster. It's also have a great optimality, but I believe it's less than Digextra. A-star also derived from Digextra. Actually, the grid best first search is an improvement of the A-star is an improvement of the grid best first search. You can check that visited more cells, because the previous algorithm falls in some local minima traps, and then the path is not calculated so quickly. And the A-star is, I would say, a fusion of the grid best first search and Digextra. So it does not fall in local minima, but in the same time it takes more time in the memory to produce the path, but also produce a very good path. And last we have the rapidly exploring random trees. That this is not a deterministic method, it's a probabilistic method. And you can see that the search is very random. Here is the goal, so now it has chosen this path. If you run again, maybe another path will be produced, and so on. It's not optimal algorithm, and it's very nice to understand how the algorithm expands and all the steps from the code. I really recommend that you go to the Robot Ignite Academy. I will share the screen again. And here, just oh no, I have opened. Okay, I have done the path planning course. They have added more courses that I didn't do here. They have a lot of great course, such as dynamic programming they explain, and they have courses of ROS 2, ROS navigation, and the path planning course I have done other courses, and it's amazing. You can learn very quickly here, so I really recommend that you go to the Robot Ignite Academy if you wish to learn in ROS and know more about robotics. And they explain step by step of these algorithms, and you implement by yourself, so you understand what's going on behind the algorithm. This is amazing. I don't think there is other place for you learn iteratively and coding and applying to the real robot. Local planners. I tested the local planners also. In the ROS navigation stack, I tested these planners you are reading now. So the elastic band. This is an emulation of the laboratory that I have done. I have begun my research with the ROS 1. So this is the elastic band algorithm. So the car had a very strange behavior, going to the right and going to the left, using the algorithm. I have used the standard ROS algorithms that I have found in ROS Week, but they were more applied to holonomic robots and differential robots, no holonomic, not car-like robots. So I had problems such this collision, the car the car got very close to the other vehicle and the algorithm didn't find a very nice solution. Of course, this is a free scenario. I'm not considering here decision making and traffic lights and so on. Just testing the path planners. Okay, so I believe this is the only feasible path planner that I have found. That's the TEP, that's time elastic band path planner. And then the car like robot was able to avoid the collision. As I have said in the beginning of the presentation, there are algorithms feasible through non-anomic and kinodynamic constraints, and this is one feasible path planner, and the other ones are the unfeasible path planners for this geometry, for this vehicle. They are feasible for other kind of robots, industrial robots that turns around Z, and not the car-like vehicle that follows the Ackermann constraint. Okay, again, this is the same video, and then the last one I have tested also the rapidly exploring random tree to check if it found the goal, and then the RT starts exploring the area, and then this is the final tree. As you can check, it's random, and this is the final path in red. Okay, now it's the tree expansion. Okay. I have also in the beginning tested the first algorithm, the first frameworks to compare path planners. That's the OMPL library, and also applications. There I go now to the I would say we need to look to the path, to the back, to the mirror, and then what I have found in the literature always was the Open Motion Planning Library, that it's a very nice library with a lot of algorithms to compare, much more algorithms that I have used in my research, a lot of algorithms. So if you just wish to test algorithms in a very simple scenario, I really recommend OMPL. Also, navigation stack and other applications, robot applications, use the OMPL classes and the instances that you are checking here. I will not explain all the classes, and you can read a paper from OMPL that you can. I also will share now with you the OMPL. That's the Open Motion Planning Library. You can go here and find the papers and found the tutorials. I have tested the A prime. I'm not finding now here. So this A primer, the OMPL primer, it's here. It's very nice because you can have a very quick benchmark that I didn't have in my research. I needed to code by hand, but in this OMPL primer you just here's the tutorial, and you can test a lot of algorithms. And then in this, it's very simple. As you can check the scenario, and you put the parameters, and then you find the feasible paths, and at the end you have the benchmark in time, for example, and other parameters. You have the charts ready very quickly. But in my case, I needed a more complex scenario than this rectangle here, this simple box. And yes, so I needed to use other softwares, but I don't discard the use of OMPL because it has a lot of planners, and it's a very I have tested with Redshift car. That is, I tested some path planners, but the scenario was really poor for what we planned, and I had some results, but I didn't put these results in my master thesis because I was testing more advanced scenarios. So I also tried to use Move It because we started our research autonomous underwater vehicle, and my professor has done a very nice work in Girona, Spain, with anthropomorphic arm and connected to the. I will just see if I have here in YouTube something or just an image. Okay, I will share with you. I have here. So Girona 500 here. So they have connected this arm with the body vehicle, and they have done an IRM, that intervention, repair and maintenance tasks, opening valves, closing valves, and they use Move It with this vehicle. So I was thinking I could use Move It for autonomous driving robots, but it was not possible because Move It was done for more anthropomorphic arms, or if, as my professor, used it for 3D environments, XYZ, and with the autonomous car we just have a 2D environment, so it was not possible to use it. The OMPL API, I have talked that I use it, but not good scenario, so I also used navigation stack, as you checked in the previous simulations I showed you of the local planners. And finally, our navigation stack also, as I showed, has some problems with the planners because they are not so suitable for the car-like robot. So I used Autoware and Apollo frameworks, Autoware AI and Autoware Auto for this research. So the contribution is that just to say you use this and use that software because it's better. I spent a lot of months and years, I say, testing all these softwares, and in this moment I say that Autoware and Apollo, they are the best softwares. Okay, so let's go to the robot operating system, ROS, the core of this research. ROS-based frameworks were selected to perform the simulations. Okay, so as I said, Move It has a lot of issues that I couldn't use for the car-like robot. Navigation stack, also the planners issue. Also, the scenario was not that feasible. It was not that real. But the first part of my self-driving cars research was in navigation stack, and I explained ROS in this framework, so you can access here. I will share with you this presentation. Later you click in this link, and you can download the PowerPoint presentation that I explain step by step what is ROS. I explain the ROS message, the ROS service, the ROS action, the URDF. I explain a lot of features of ROS in the self-driving cars context. So if you know anything about ROS, you can just download here and learning with ROS used in a project. So it's an easy way to understand ROS. Not the only way. The other way is learning with ROS Week and the Robot Ignite Academy, as I said. And yeah, it's this. In the future, I will prepare a presentation of this PowerPoint here, and I will make available in YouTube. So subscribe to my channel. You will get very soon this presentation. And okay. So the navigation stack architecture here. We have the global planners, local planners. We receive data from the map server, then sensor sources, the AMCL algorithm that's for localization. And we have the transforms, the odometry source, and at the end we receive the goal, and at the end of this processing, the robot send commands to the base control, and then the robot starts moving. As you can check, this is a very nice architecture for a lot of robots, but not so specific for self-driving cars, where we have some specific features should be addressed. This is the reason I use the ROS-based autonomous driving stacks, because the architecture is a little bit different. As I said in the beginning, we have in the autonomous driving different and specific tasks such as lane detection, traffic light detection, object classification, and etc. And also in the planning we have different plannings, the road planning, the prediction. We have the behavior planning that switch between the global and the local planner, and each sensor here is closely related to the function. So as we said in the implementation I have done in Autoware Auto, the camera is responsible for lane detection, traffic light, but the GPS is more used for the localization task, for example. This is okay. So in this architecture we also have also we have in this, sorry, my cell phone has triggered because I said something and it understood that I was talking with him with it, sorry. Okay, so here we have the driving monitoring, and we don't have this in the other robots. So in ROS navigation stack this cannot be done. We have V2X communication, that's the car communicating with other, the correct name is V2N, I think, because the car communicates with the traffic light, with the satellite, with other vehicles, and with cell phones, and it receives information from a lot of agents, I would say. And so if you use the sensor and then again the decision making, planning, and then the actuators, it's quite similar, but there are different and specific tasks that navigation stack doesn't cover, but it's a very nice beginning. So I really recommend that you start by navigation stack if you wish to understand and very deeper, step by step, and then you can improve your skills with navigation stack, and then later you will manage easier the Autoware Auto and Apollo Auto. This is the reason I have delayed my master. I have used about 2 years to finish all my master thesis, do an internship in ADAS, but also because I tested all the frameworks from the literature that I have found and was open source. But I have learned a lot, so if you can also do the same, and you understand very easily the Apollo and Autoware, then you start just from Autoware and Apollo. Actually, there are steps you can follow. I will share with you now the steps. The construct has how to start with self-driving cars using ROS. If you type this in Google, you will find this step by step. They have Ricardo Teles has written this, and he's an expert in ROS. And if you wish to go to autonomous cars, you start. You has a tutorial here, so start with navigation stack. So step 1, then you go step 2, that is ROS in 5 days, I believe, and you go to step 3 and you test the ROS autonomous vehicles 101. I have done this course, it's pretty nice. And then if you have some time available, you can build this city in your bedroom and test it. I didn't do because I didn't have many time available. You can test in Ductal simulation, they have also there, and then later you go to the Autoware project or Apollo. And yeah. So don't start here, because if you start directly here, you have a lot of issues if you don't know anything about ROS. Okay. So let's go finally to the where we wish to arrive, that it's the autonomous driving stacks, that Autoware. And Autoware, it's a framework, it's a software that able to do 3D map generation, localization, perception, planning and control for autonomous driving. This project started in Nagoya in Japan, then later here's the sketch of the Autoware. It's very similar to the structure that I have showed you. That's the recognition, judgment and operation that I have done for all the robots. In that review I showed you, and here is for the self-driving car. So you have lane keeping, object detection, brake and steering, acceleration, planning, and they have the communication from the software with the actuators that is doing between using the CAN. This is the protocol of communication that it's a multiplex messages. So also in Robot Ignite Academy there is a course that explains detailed this protocol and this channel of communication. And here is more to the software side. What you need to run Autoware: you need a very good GPU, you need use Linux, you need to use ROS, you need to understand a little bit of Docker, and also the other features are such as hardware and the ADAS and the other layers of the Autoware autonomous driving text, the electronic control unit that will manage the actuators and the messages from the actuators, from the sensors. So it's a very complete autonomous driving stack, and you can check all this architecture in the Autoware Auto course, as I said. Okay, Autoware AI. Autoware AI was an improvement of Autoware project, and it's managed by Apex AI now. The Autoware AI has a very nice friendship interface with the user, and this project now is it's being sponsored, and also there are a lot of companies and also non-profit members, universities that improve the code, improve the software. As you can check here, Empotech, Apex AI, Nayoga University, Open Robotics. So a lot of people working in an open source project and package to improve the framework. I have already showed you this course. Here's the link if you wish to access. The architecture is pretty similar to the previous I have displayed. That's the perception, localization. We will focus in navigation. Then if we go here, we have the global planner, local planner, but also the decision making. The global planning Autoware is called mission planning, and the mission planning is a high definition 3D map. As we said in navigation stack, it was not possible to use the high definition map, and the local planner is called motion planning. That calculates the feasible avoidance trajectories, and we have also the decision making that decides if the car can, after the vehicle calculates, after the trajectory planners calculates the trajectory, the decision making say, okay, you can follow the trajectory or not because there's a traffic light in red, or there is a pedestrian, or this is a near to a school, so you must wait more, and so on. It's more complex than navigation stack. Okay, I wish to show here in my Linux, I run it here in Docker, the Autoware runtime manager. That is the interface I was talking about, and this interface you can manage better the packages you wish to test. So if you are a researcher of perception or control field, you can test different perception, sensing, and different packages. Here I am just loading a mapping package from that Autoware provides. I don't remember which city I have tested. Here you can see 7 or 8 cities that are available. I have used LG Simulator, but I think with Carla it's also the same maps are available. I have triggered map. As you can check here, the consumption of the CPU. It takes a lot of CPU. Okay, there the sensing algorithms now, the tracking algorithms, the LiDAR detector here. You can manage and tune the parameters to make the smoother and optimize the planners or the perception. You can select different mission planners to test, motion planners to test, and not all the planners were working when I tested, and they always launch a new release of Autoware. The Autoware AI project, I think this was the last year they have launched the last release, but Autoware Auto, I believe they're more, it's newer. Here's a map from San Francisco, very huge map that you can test and play. Here it's the RVs, that is the ROS visualization tool. You can visualize the map, and I don't remember if I have this. Okay, you can focus in the map. You have some tools here in the RVs, and yes, I think it's this. Okay. So what's the mission planning? I have used the mission planners available on Autoware AI. That's the A-star algorithm. The A-star algorithm uses this heuristic function that it's A1 and A2, the alpha, it's the coefficients, the F is the heuristic. This is more explanation for my master thesis, so you don't need to pay many attention if you don't want to understand how the path planners work, but if you be interested in path planners, so I will explain. The GI is the cost to reach the final waypoint. So this is the total cost, I would say. So the aid is the estimate cost to reach the final A point, so it's the estimation. And here's this from the origin. And the A1 is the distance between the point. I forgot to write one here. This is the A1. Distance between the point I and the guideline that I will show later. That's the literal distance. And the A2 is the longitudinal distance from G1, GI to the target. Not from the origin, but for the point the planner is calculating. So alpha 1 and alpha 2 are coefficients to penalize the moving in specific direction, increasing or decreasing the weight from the aid cost. So if you wish to penalize the lateral to the left, we can increase this alpha 1, and then the heuristic function will say, okay, it's very high cost to travel to this point. Then if you have a F2 that has a smaller cost, because alpha 1 is smaller, or I'm sorry, or if all the sum of these terms are smaller, then this F point this heuristic function will say, okay, choose this point and not this point in the lateral, because it's more expensive. If you understand now with the image, so the target here, the G is the total cost from the origin, so from here to here, and then the aid is the A1 lateral, and the AD2 is the longitudinal. So if we should penalize a point to the lateral, we just increase or decrease alpha, and in this way we choose a more safety or more close maneuver here in the green points, because we select the green points based on the value of the heuristic. A higher value will be discarded. So the A-star algorithm this modification works like this from the A-star algorithm that I have displayed in the beginning, the global planner section. So motion planning. For motion planning in Autoware AI, I use a hybrid I-star and the modified lattice that they just have adjusted the standard A-star and lattice from the literature that I explain in my thesis that I will make available. They just modify for non-holonomic robots. So here we have for a normal robot, but a car does not go to the diagonal. So in the figure in the left, we just check that they have added a turning radius to the left and to the right, and in the right figure we can the trajectory cannot be to backwards as in the bottom of the image, but just to front of the car the planner can be expanded. So they have adjusted to the planner to extructed environments, because in the literature review the planner was used to unconstrained environments. So they have just adjusted the path planner for car-like robots. As I said, the planners are specific for geometry of the robot. Does not exist an universal planner that works for all the robots, for all scenarios, and so on. This is how it happens. Okay, this is the framework. This is the ROS graph. If you open a ROS bag, you see all the topics communicating between them. So the rectangles are ROS topics, and this circle, the ellipse, they are the packages. So here we show how the path planner. We have here the global planner, that's the A star, the free space planner. So this free space planner calculates waypoints, as we have seen in green, that they are called final waypoints, and sent to the control algorithm that will calculate the control commands to send to the vehicle here, or using CAN protocol, or will send this data to the simulator through the WebSocket bridge, the ROS bridge here, simulator from LG that I have used, but you can use Carla or other simulator, Gazebo for example. I used LG because it's more realistic and has a very good, very professional support that answer very quickly. And they also receive data from LG simulator. So we receive data, point cloud data, for example. Then ROS process this data and says the current pose of the vehicle, do the transforms of the environment to say where the car is and where the obstacle is. In ROS you filter this point cloud, because we have a lot of point cloud data, so you need to remove you need to remove the ground and to remove and to use a threshold to remove the objects above the specific 8. Then we have the cost map generator that generates an occupancy grid map, and in this occupancy grid map we have assigned it if there is an obstacle or not in a specific grid. 0 is it's free, there is no obstacle, and 1 if there is obstacle. This is more complex because we have numbers between 0 and 1. We have false positive and false negative, so it's not so easy. That's why in a lot of algorithms and decision making algorithms to say if there is an obstacle or not. And based on these obstacles, the local planners here receive this data and calculate safety waypoints and closest waypoints, and then you have then it sets the then it sets the velocity, and this velocity to obey the kinodynamic constraints, and then it sends to the final waypoints here. And these final waypoints, then if we have previous final waypoints from the global planner, but now some final waypoints were removed because the car would collide with the obstacle. Then the A star avoid the hybrid A star calculated new waypoints, and these new waypoints now are the final waypoints. And these waypoints will distort the global waypoints, avoiding the collision. The new commands are calculated, and this is the cycle. If you have a real car to test, you can test with Autoware. Otherwise, in my case, I have just used the simulator. And this is how is the integration of Autoware with the simulator of the real car, and the integration of the path planner in ROS. The same one for the lattice. I have the free space planner here, is the global planner. This is an outline of the ROS bag. If you wish to open a ROS bag, you will see a figure, I would say twice or 3 times or 4 times bigger than this. There are a lot of topics and packages and in the ROS graph. So I have just removed some package and topics that were not so important in the path planning context. This is not all the ROS bag. It's much bigger than this. So here's just for you understand that the local planner distorts the global planner final waypoints, the trajectory waypoints, and of course it local planner has a different package to calculate safety waypoints, but the idea is the same. At the end, the final waypoints are distorted or changed. And the algorithm here, I have used the pursuit control algorithm, but you can use the MPC or other. The focus of my master is not testing the different controllers. In my master thesis I have made available the other papers that I have read, and they discuss more the control algorithms. And okay, for Autoware AI, this was the integration. Also in Autoware AI, I have used the Open Planner that we can check the architecture here. The Open Planner is more complete, I would say, from the previous planners, because it has already the local planner and the global planner and the decision making, the behavior planner inside this planner. So it is able to get the HD map information. This is very nice. And here is the architecture. As you can see, traffic light info. So the planner interprets the data from traffic light. The previous planners, they don't interpret the information from the HD map, so they are not so complete, the local planners I mean. And these planners, you have everything already integrated. This path planner is from Hatem Darvish from Japan. You can, in my paper I have cited it, you can find the planner and the paper and also tutorials in his GitHub. I will make available also in my YouTube description later. Okay, so steps for generate the local trajectories. The global planner's address, it gives us, it provides a center global planner here to the center of the lane. Then later the rollouts are produced that are offset of this main lane, this main trajectory in the center. It will always say to the car to stay in the center of the lane, and then the rollouts will guarantee a possibility for evasive maneuvers. This is how these are the rollouts that the Open Planner produce using the local planner. So if the obstacle will be in the center, the car is going to use a left or right rollout to deviate from the obstacle. Okay. So now I'm going to explain the trajectory generation with Autoware AI and LGSVL simulator from the Open Planner. Sorry, It's very similar to the other planner. The only difference is the behavior selector that interprets data from the HD map. As you can see here, lanelet map feeds the behavior selector. Also the local planner sends the local trajectory cost and the weight from the trajectory that it has calculated. So the behavior selector process all this data and say, okay, use this rollout or use the center, keep using the global planner, there is no obstacle, and then also delivers and provides the final waypoints. Then again the same structure sent to the controller, and it's this. Okay, so Autoware Auto was tested after Autoware AI. Autoware Auto is safer and it runs faster than Autoware AI because it's based in ROS2. In ROS2 we have a quicker and relying data distribution service. But Autoware Auto covers specific scenarios. So it was not possible to test in different scenarios. The architecture of the planner is quite similar to Open Planner but different from the other ones. So the Autoware Auto use the perception data, point cloud fusion algorithm, voxel grid downsampler to eliminate some not useful data from LiDAR, point cloud map, and the lanelet 2 map. That it's lanelet is the format of the high digital map, and the behavior planner for the AVP planner that was available switches between the lane planner and the parking planner. That is, there are sub planners. In other words, the parking planner is used to park the car and the lane planner to follow the lane to find the suitable parking spots. Because the first ODD covered the parking scenario, this is why we have just the parking planner and the lane planner here. And then the object collision estimator says if there is obstacle or not. Then the behavior planner decides which planner to use and which command to send to the MPC controller. The MPC sends the commands to the vehicle, and the vehicle moves. So we have the mission planning and the sub planners here. The sub planners always switching between them because the car is always looking for a suitable position to park, and in the same time it's moving forward. You understand later when I show this simulation. So Apollo Auto is developed by Baidu, and it uses CyberRT communication protocol instead of ROS, but it's very similar to the ROS. Use services, actions, and topics. The architecture very similar also. As they have just this the Guardian, that it's a safety module they have added to control the control module and deliver more safe data to the channel, to the CAN bus. Okay. So the Apollo Auto planning, it's a planner composed by 3 layers. The first layer deals with the lane determination. The second, there's the motion planning. It's decoupled. It optimizes the path and the speed profile with dynamic programming and quadratic programming. The dynamic programming and quadratic programming you can also check in the. If you want to understand better, you can just come to this video here. That it's reinforcement learning for robotics, dynamic programming problems, ROS developers live class, and
find out
Alberto explains the dynamic
best path, which means the minimum code
programming.
path from the red node. Let's start from top.
It's a very nice way to understand dynamic programming, quadratic programming. And the third layer covers traffic regulation and decisions. So the same of Autoware, it also is decision making. And here is the structure. It's also explained in my paper, in my master thesis, if you wish to understand better. So the coped speed and path optimizer strategy for smoothing the planet. The first layer selects produce this trajectory in purple, and later the second layers lets the trajectory more smooth in speed and path profile. And then we have this pink trajectory here, avoiding the obstacle that's in the left of the car. The trajectory introspection, similar to the ROS bag. In Apollo we don't have a ROS bag because Apollo has 3 releases, and the last release they don't use ROS, it's cyber channels, and here is the dynamic and quadratic programming layers, and the decision making tasks, and here we have the final trajectory calculated, and yeah. So let's go to the simulation setup. I was not able to use my private notebook because I didn't run Apollo and Autoware, all the modules, just some modules, and then I was not able to simulate everything. Then I needed to rent a cloud computer to run these softwares. I can suggest you use Paperspace. I have used it, it's very intuitive to use. I will share my screen then for you to check. It is the website from Paperspace, and it's cloud computing. Then you just do an account here and pay per hour. The price are accessible. For students, I really recommend. You can create your machine there with the specifications you need and just use it. Okay. Okay. So let's keep here. After I have displayed the Paperspace cloud computing, and this is my configuration, and just the operating system here it's wrong. It's Ubuntu 18.04.5, not 10. My operation system. Okay. So let's keep here. I have used the LG simulator, as I said, because it's more realistic, and we have the Python API to program the scenarios. We have a lot of different sensors and plugins. Also the support, as I said, it's pretty good. And then you send data to the autonomous driving stack, that can be Autoware or Apollo here, through the bridge. That can be the ROS bridge or cyber bridge or a custom bridge. You can also develop your bridge, your software to process the data. Of course, ROS and Apollo, it's developed by a lot of other researchers, so you can reuse their packages, then do everything by your own. But you can do it, and then later then the control data returns to the vehicle or to the simulator. It depends from your lab. Okay, but in autonomous driving we need to test the car in the relevant or critical scenarios to validate the functions. So the researchers and the automotive companies, they test the scenarios in different platforms, simulation platforms, to validate the autonomous driving functions, and also in their vehicles. But nowadays they are not testing just to driving thousands of kilometers to validate the functions, because the car can not face the most critical conditions. You can drive from Germany to, I don't know, to Russia, and maybe you don't find a critical condition that the car will fail. And if you test the critical conditions, you can test in the simulations. You can put a very harsh condition regarding weather or regarding an agent, another driver. You can put snow, and you can put you can make it rains in the simulation, and programming hard conditions for the car avoid obstacles. So this is the research groups do. And one approach that I have read and I found interesting to put in the master thesis presentation was the ontology-based approach. The ontology-based approach that is you use machine learning to find the critical scenario. So they have changed the slope of the road, the surface of the road, if it's wet, if it's dry, if it's icy, the type of the lane, the amount of the lanes, also the agent behavior, the position, the speed, so you can increase, decrease, and then you do in the simulations the test. If the car passes, it's okay, the algorithms are working okay. If the car fails in this condition, okay, so this is the critical condition. So I need the group need the automotive industry needs to improve their algorithms, or the researchers, to work in this critical condition. So implement the algorithm again, fix the code again, and test again the function. So okay, now in the same harsh condition, the car avoid the collision, so it has passed it. So now it's fixed. So this is a kind of infinite loop that the automotive industry must always do to finally, and then the final goal is the car always pass and never fails. So the function is validated and approved because it faced the most hard conditions and has been approved in all of them. And they use it in this method, machine learning, to combine a lot of different parameters with different values, because if you do this manually, you will take a lot of years. Also, their method, very important, that the automotive industry has joined their efforts to develop, is the Pegasus method. That it's a method also sponsored for the German government to decide validation method and method to determine the critical scenarios. It's a very huge manual, sorry, not so huge manual, but a very, very good manual. If you are autonomous driving research, I recommend you read this. And I will not go into detail here because it's really big. You just type in the internet Pegasus method and you find it. And it's an effort for the big enterprises, a big automotive enterprise such as Audi, BMW, Mercedes. And this method has also, they have also done some meetings in Asia and the United States, so they are expanding. I would say the other countries can also use this method and to validate autonomous driving functions. It's very complete. So now, okay. So for my research, I have read these manuals and papers to select the relevant scenarios, but I have also found in Apollo Auto framework the Dreamland. The Dreamland, it's a place, it's an application that you can use as researcher in Apollo in Baidu website. And they have a lot of scenarios, sample scenarios that you can check there in this link for your research. I have visualized more than 100 scenarios, very nice for testing, and I will show one here. I found interesting. So here they have the scenarios in the left. Different scenarios, intersection and static obstacles. So here you activate the modules that you wish in the perception phase, in the prediction, planning, decision making. So you can activate and deactivate the modules and test them in this Dreamland that's from Apollo as Apollo software. They have also a paid version, and some features are exclusive for China users. I was not able to access them, but I mean it was very important for me to decide which scenarios to test, because I have checked one by one, and they have very nice scenarios, that very challenging scenarios. That's interesting to see how the car behaves using Apollo framework. The link, sorry, back here. Sometimes this link didn't work. The link works, sorry, but sometimes I have opened it. I will share with you now. Just one moment. Yeah, okay. So I'll translate from Chinese. Okay. So here. It's written in Chinese, but you can there is also an option to translate, and you can log in with GitHub, and then you go through that. But now I'm facing some errors. I don't know if I have select the wrong navigator. So let's back to the presentation. But you can try it. It works. You can try that link I have. You can try that link I have. I will make available this presentation. Just click in that link and you will redirect you there, or just type Dreamland Apollo in the internet and you find. And you just need to sign up and start using. Also, as I said, have some paid versions that use machine learning, and you can see how your algorithms work in specific scenario, and there are quality measurements. It's very nice, but it's complex it's a little bit complex to work with, I believe. But as I said, I didn't test because it's a paid version, and you also need to log in China or send an email asking for authorization if you are a non-China user. Okay, programmed scenarios. Then, using all the literature and the Dreamland, I have decided which scenario should test. Also using the time to collision metric. That means the car is 1 second to collide with the following car. So this is a good metric to decide that this scenario is critical, because a huge time TCC means that it's not a very critical. It's not a critical scenario in terms of collision. Of course, there are other criteria, and you need to be an expert to decide which scenario is critical. As I didn't have a machine learning code, or also I am not an expert in this area, I have read and seen the scenarios I showed you in Dreamland, and I decided to program my own scenarios. And I have tested a parked truck scenario where the truck was avoiding the car navigates in the road, because it's almost in the middle of the road. Stop it. So the car needs to recognize that it's not that this car is not moving. Also pedestrian crossing, I stop and go, that the car in front stop and go and stop and go and stop and go. So it's always braking, and your car in the ego vehicle must always brake or overtake. So it must decide what to do in this situation. And the cutting, that the other car from the other lane just cutting in front of the ego vehicle. Okay. So here's the programmed scenarios. I have used this map that was more simple. And then this is... I tested that in the cutting. I tested in this. I don't know why it's open every time, this window. My God. I'll show again. Okay, so okay. So here are my tests. I have tested a cutting scenario, and the car was overtaking over the curb. So this is totally wrong. Was not safety maneuver, so I had a lot of issues testing dynamic scenarios, and I needed in the time I need to finish my master thesis as soon as possible, and then I decided then later for not. Just let me go ahead. Because the decision-making module was having strange decisions, such as I've seen, going over the curb to overtake the car. Here also the car has stopped infinitely because of the traffic lights and the signs. The planner calculated that it should overtake, but it didn't. And this is why I stopped to test dynamic scenarios and complex scenarios with a lot of HD map information. And then I unfortunately I needed to test to compare the trajectory planners just in the most basic scenario. Okay, there was a video here from the other implementations of dynamic scenarios that I have said, from the pedestrian and the other ones, but I have done this presentation in Prezi and I have coded something wrong that this video does not appear now, but no worries, you can check later in the description. I will share this presentation, you can check later the programmed scenarios that I have done. Okay, so in my scenario I have a road length about 100 meters, exactly it's 80 meters and something, but I put 100 to make easy the reading. Okay, as I said, the dynamic scenarios have faced a lot of problems, and I just used the parked truck scenario to compare the path planners because I didn't have time. I needed to finish my master thesis and I didn't have time to fix the planners and the decision making to go deep in this to test the dynamic scenarios. Okay. So at first I tested the free space from Autoware AI and then with the hybrid A-star path planner, and this is the behavior that I had from the car. The car stopped a lot of time waiting for the overtaking maneuver. Exactly, I believe it's 70 seconds. It's a lot. And finally it has calculated, the local planner calculated an avoidance path. And this is the behavior we would have in the real car because the LG simulator simulates the real vehicle. So this path planner was not that fast as you have seen, but found the road, deviate the obstacle. And later I tested with the lattice. I tested the hybrid A-star path planner, global planner, but now with the lattice motion planner, and the behavior was quite similar in terms of lateral distance from the obstacle, but it was much quicker. The local planner calculated the road much quicker and avoided the obstacle again. And yes, as you can check, the tree hold, it was different. One planner calculated that the goal point was a little bit ahead, the crossing, the stop sign, the other before. And as I said, the first path planners didn't obey the HD map info. And this was the open planner. It was better in terms of safety because, as you said, the car changed the lane to overtake the vehicle, and then it has returned to the center of the other lane and stopped before the stop sign, because the behavior planner says, okay, here we have a stop sign from the map, you must stop. And we check it here in the end of the video. We can check that the local planner that the local planner is drawn in green. The global planner is in blue, and then the final waypoints are distorted. We check in the right side of the figure here. I think now it's going to draw the green. The local planner is this green planner. In RVs we can see. Finally I tested the Apollo planner, that is the public road. The framework is a little bit different. We can check here the box, the bounding box from the truck with the speed and the width. And the public road planner was much quicker and smoother from Apollo Auto framework. And the LG SVL interface in the right side. Okay. So now I have done just a bird view record, just to say a feature, show a feature of LG simulator that you can. This is a plugin that you can put the camera over the map, over the city, and this is the behavior of Open Planner. The car is stop and go, so it's not so comfortable for the driver, I think, but it has avoided the obstacle. And here we have the usage of Open Planner for its creator, Hatan Dervish. This is the Open Planner, and the car is driving autonomously in this. I think in this scenario. So just to say, in the simulator is almost the same in the testing the real vehicle. The software is the same, and the idea is the same. And now we have here the bird view of Apollo planner, that it's much smoother and quicker, as you can see, than Autoware AI. And just check here just 1 minute. This is Apollo video. In a real city, using the framework, using Apollo. It's much stable, as you can check. Recognized traffic lights, avoided obstacles. And this is another open source framework that they are using. Baidu is using in China this software. Just let's go ahead now. Okay, now I have tested the Autoware Auto. I have tested Autoware Auto autonomous driving stack. but not in the same scenario, because Autoware Auto, as I said in the beginning in this presentation, Autoware Auto was developed for a specific ODD. In this year, they are working with the cargo delivery in airports, if I'm not wrong. And in the beginning of this year, they have added just the autonomous valet parking, and I was able just to test this path planner. So it's this. So let's park the car in this final journey. So here is the simulation using LG Simulator. As I said, the car is trying to find a spot here, so it's switching the lane planner and the parking planner. Now the parking planner was triggered because found a spot to park the car. And of course, this spot I have selected programmatically, or in Arvis, you can just select where you wish to spot the car. And then you also can get out the spotting with using the same planner, and then switch to the lane planner and the global planner again to find a new place to spot the car, to park the car, and so on. Also a video now from this feature. Okay, very nice, right? Okay, so at the end we need to understand that's the goal of the master thesis. How good are these frameworks and the path planners? What's their performance? And then I have extracted the data from the simulations and done a benchmark, with exception of Autoware Auto, because in the moment I was developing the code, there was an issue with the communication between Autoware Auto and LG's SVL simulator, because LG has done an upgrade in the simulator, and then the communication changed, and they just fixed this now, and I have when I have finished the master thesis. So unfortunately, like I couldn't extract the data from the parking simulation, but I was able to record at least. So these data are the comparison from Autoware AI and Apollo AutoGist. So the trajectory profile, I have used Plot Juggler, that is a ROS tool that has won the ROS Award of the year. It's very nice tool that you just read the ROS bag. So you take the ROS bag data directly, and here is the path from the 4 path planners that I tested. As you can check, the open planner that changed the lane, this is the draw of the trajectory, and the other planners, Apollo in green, and the other planners. Let's go. So the free space I star, the number of waypoints calculated, the Apollo number of waypoints I have also calculated, I have extracted this data. So go to the lateral displacement. The path planners have moved it to the lateral more and less. As you check it, the open planner has had a bigger displacement in the lateral side. If we integrate the area, taking the center lane as basis, we have this value for open planner, this value for A star, motion planner for let's see, and public road, that we had a less lateral displacement. Open planner has opened a bigger distance from the obstacle and from the lane. Okay, so let's go to the total distance traveled. We have open planner traveled 82 meters. Also because of lateral displacement, the path was bigger, and the shortest path traveled was from lattice. So that's in terms of length of the path. Lattice was the better. Distance from the obstacle, I have used the rear left point here as the basis to calculate the minimum distance the car was traveling around the obstacle, because as we have checked, the overtake happened in the left. So this is the closest point the Eagle vehicle stays from the obstacle. So the calculation of the minimum distance was based on this point. And here we have the distance. So on the open planner was the highest distance. So it was more safety, I say, because the car traveled not so close to the obstacle. And the free space lattice, the car traveled very close to the obstacle. And here is the drawing. So it begins far from the obstacle, and this is the position that extracted with Velodyne data that where the obstacle was in the middle of the road, in the 40 meters position next. So, and then the car again in the right side of 40 meters goes far away from the obstacle, so the distance increases again to 15, 20, 25, 30 and to 40. Okay, so smoothness of trajectory, it's important quality of parameter to measure quality and comfort of the trajectory, because it measures the jerky of the trajectory, that it's the derivative of the acceleration. So the smoothness of trajectory, at first you need to find the jerky, that is the derivative acceleration, and then smoothness is the integration of the jerky in square of the jerky. sorry, not the square, the power of the jerky. So the values are here, the smoothness trajectory, but as the smoothness is the pole of the jerky, then the highest value actually is the less smooth trajectory. So that's why in the right side of this chart I have done a factor conversion to say, okay, public road was the most smooth trajectory because it has the shortest value of the pole of the jerky, and the lattice and open planar was the most jerky trajectory, so was the less smooth trajectory. And as you checked in the video, and also in the trajectory planar's profile in the graphic 1 that I showed you, you can check that these planars has a more oscillation in their graphics, and public road was more smooth. Okay, so the trajectory execution duration and about the time in seconds. As we have seen in the first video, the A star took more than 60 seconds to decide to overtake the truck. Then later Latsi, open planar, and the public road that from Apollo was very, very fast. Less than 20 seconds compared to the others were very, very fast. It was faster. And the other parameter was the consumption of energy. That's in terms of power, that it's that the work that a machine, that the engine does, divided by the time. This power was measured in each timestamp, in each millisecond, in each data that in each row that I have extracted from the ROSBAG. And the public road has this value, but open planar was the one that consumed more power, where the engine consumed more power because maybe because the path was higher, and then later public road because the power is also related to the velocity, and public road has delivered a higher velocity, so the power also increased. And these ones has the less value for the power consumption of the engine, and also calculated the friction power because the negative acceleration, when we calculate here the force it's equals to mass and multiplied by acceleration. So the negative acceleration is regarding the friction of the car. Of course, the engine does not consume energy to brake the car, but the friction power is being in some researches, and they convert this energy, the friction energy to the car. So this is why I have calculated here also the friction power, and the same structure is followed for the engine consumption while the car is acceleration. Also OP, if we check in the video, the open planar has braked a lot, and as I have commented with you, look, the car is always braking. It seems not to be very comfortable. So the value of the power also increased here if you check. Okay, so path tracking error. This is more regarding to the control, but I have also plotted because I found interesting. It's how much the trajectory was feasible to the control algorithm, and we have the distance to the path in XY here, and we can see that that the public road, that is the Apollo autoplanar, it has the biggest deviation. I believe that it's because it performed a bigger, developed a bigger velocity while it was running. So this bigger velocity, it makes harder to track each waypoint. So this is why I believe it's the higher deviation. Then later also OpenPlanner, we can see that OpenPlanner has had the bigger deviation when it avoids the collision and it's returning to the path. And here's the deviation in the heading, in the yaw angle. So also OpenPlanner had the big deviation because it has really deviated, had a bigger deviation, had a bigger evasive maneuver in the lateral terms. I say it traveled to the left lane and the others didn't. So this is why it also had a bigger deviation in the yaw angle here, but not so much, because if you check, there is less than 1 radian, and here it's in meters, in XY. Okay, so let's go to the vehicle behavior. Here it's the chart that represents the velocity, the acceleration and heading, the velocity profile. As we see, the public road have developed a bigger velocity in blue. The acceleration and the jerky was bigger in the A-star path planner, but mainly in lattice path planner. We can see the oscillation here in the acceleration, that it's in red. And if we go back to the smoothness of trajectory, we will see that Letzi and A-star was not so smooth, and we can see here because of this oscillation. And here in the heading behavior, again the OpenPlanner has presented a bigger heading deviation, not deviation, but behavior. And Apollo was more smooth, as we can check here. And the other ones also didn't change the heading angle too much. And because of this deviation, also the OpenPlanner was not the most smooth path planner, but also was one of the most jerky. I have also measured the computational effort, because it's important to understand which path planner will work with less computational resources. And regarding the CPU, that's the arithmetical units usage, we have that the public road consumes a lot compared to the other planners, and OpenPlanners consumes less CPU than the other ones, and the Apollo, it's the one that consumes the big. Here the usage of run, it's about the memory that the algorithms use. But not just the algorithm. Here is all the framework. It's all the modules. But as I was using the same perception modules or similar modules, localization, etc., we can have an idea how much memory the platforms use. The Apollo used a lot, it was about 20%. I mean a lot, because I had 60 gigabytes memory in this rented computer. And so it's a relative, it's how much your machine has memory available. And OpenPlanner used 10% about, then Lattice 12, and also A-star 12, and this is not too much compared to Apollo. Also Apollo here is the biggest in memory and in CPU consumption. Okay. So now I hope I'm going to the conclusion. I hope I have covered all the I hope I have covered all the interesting topics that you as researcher and student would like to see. And I'm going to the conclusion now. That is, I have done a table based on an article that has also studied Autoware and Apollo frameworks. This number is from my thesis. Then you can check later which article I have used. And I have compared in mapping, localization, perception, planning and control modules. And I say which one is better. In Apollo, mapping was better, localization was working better, perception was not working, it was working better in Autoware. And then I needed to use modular bridge in LG. I'll not explain now, you can check what is modular bridging in LGSVL website. And also the planning and control, I also compared them, that I think it was better in Apollo Auto. So, but this is based on my simulations. Maybe for other simulations this change a little bit, not too much I believe, because mapping in localization in Autoware, it has a lot of failures. When I tried, I was not able to simulate the Autoware auto simulations in San Francisco City, for example, that has bigger maps, just in Apollo. Also planning and control, the path planner also calculates in 90% of time the same route in using Apollo, and in Autoware less than half. Sometimes the planner is one, sometimes it calculates other trajectory. It's not so robust, and here is not so robust. In agreement with this article, it's moderate but high in Apollo. Then you can just use this table as basis to decide which autonomous driving open source stack you wish to use. And it will be, of course, an open discussion, because the simulations and the used models will change. I focus in path planning, but I also use the other models because it's mandatory to use. Okay, the evaluated metrics, it was based in my research and the benchmark I have done. So passenger comfort, I have assigned 5 to the best path planner and 1 to the worst. So the safety maneuver collision risk was very bad to the free space lattice, because the car was very, very close to the obstacle. And the best was open planner. It's inverted, sorry, because the car was very far from the obstacle using open planner. So it's 5 here, not 2, and 1 for free space. Then computational effort. The worst one, as we checked it, was public road from Apollo, because it needed a lot of computational resources. And open planner was the best, and this why 4, because it does not use a lot of CPU or GPU or run memory. And then you can just check later which planner is the best one. So also in the autonomous driving or robotics, we have good planners for specific tasks, bad planners for other tasks. There's not an universal planner that is the best in everything. So you need to be careful to understand which path planner is the best to use in specific scenario. That it's for the parked truck scenario that I have simulated, as you check it. My future challenges is implementing my old trajectory planners, because I have just tuned it, used it, and modified a little bit from the other planners to work, but I have not written my old trajectory plan. And of course, testing a real vehicle, because I think it will be amazing testing a real vehicle. But I was not I could not afford one real vehicle. And before I finish this presentation, I forgot to show the GSVL simulator that I'm going to share now, the Python API. And I think it's interesting to show you the Python API here, and you can create your vehicle, the pedestrian, the other agents. You do everything with Python, the scenarios, the different pedestrians, and the NPC. And I really recommend you read the tutorial from SVL Simulator. It's a good start. And now I'll go ahead now with if you have some question, of course you can send me in the commenter, or and if you need some basis for your simulations, I have provided all the code of extraction of the cyber channel data of the ROSBAG. There are some tutorials, there are some code that I use the path planners in my GitHub repository. You can subscribe or just access it. And if you need additional data, you can send me an email or reach me in LinkedIn. I don't know. I will share here. I share also some projects that I have with autonomous underwater vehicle and other features here. Also in my channel in YouTube, for example, I post some videos. One video that I have posted from my undergraduation course is this video here. I post some videos that this is from my this is I have done this in my old car to change lift of cars. So I have used some pistons. This is the video that I have done in my old Volkswagen. So I mean, if you like engineering, I have interesting videos there, so you can just subscribe. And okay, so now okay, so as I said, you can reach me here by email or LinkedIn. You can take the code, change it, reuse. You'll be very happy in answer some doubts. And it's this just before finishing this presentation, I'm very grateful. I would like to say that I'm very grateful to Germany and German people. They're incredible, and I have made available a video in this presentation where I tell my experience in the Technische Hochschule Ingolstadt, and also my experience in Germany. If you are curious and would like to study in Germany, I really recommend you study, work, and do an internship there. You will learn a lot. It's the origin of technology, automotive technology. I think it's in Germany, and it's really amazing. So if you wish to watch the video, I will will share with you now, but you can also find later in the description of this video the web link, because the video is very huge. And yes, this is the university that I have.
Hi, I'm Marcos from Brazil. I am a mechanical engineer which currently focusing my master in robotics field.
And this is the university that it's pretty big, pretty technological, amazing, amazing. You can check here later. It's a nice video, I think.
My research with autonomous Autoware.
And yes, that's it. Thank you very much for your attention. Now I'm finishing with the credits, and I hope you like it.
You might be missing some of the benefits that stereo can provide.